the dot product. Mathematical definition: if we have vector A equal A1, A2, and B equal B1, B2, then the dot product of A and B is A dot B, and we combine their components. So we have A1 times B1 plus A2 times B2. And notice that we started off with the vector, and we did this dot product process, and we end up with a scalar. The result of a dot product is not a vector, it is a scalar. A lot of my students are asking if this means we are multiplying two vectors. Actually, there are two ways to multiply two vectors. We can use a dot product or something called a cross product. So you definitely want to specify this is A dot B. You don't want to say A multiplied with B or A times B. It's A dot B. So let's actually try an example. Find this dot product. We have 3i minus 7j times 4i. Now remember that if I write i's and j's, those are unit vectors. That's my linear combination of my standard basis vectors. So I can rewrite this first vector in terms of its components. So I have 3i minus 7j becomes 3 and negative 7. And I'm dotting it with the vector 4i, which means I get 4 comma 0. To do the dot product, I take the two x components, 3 times 4 plus negative 7 times 0, and I get 12. Here's some properties of vectors. If I have A, B, and C as vectors in the plane or in space, so this could be vectors that are two-dimensional or three-dimensional or more. Remember, I can always add another component. And C is a scalar. Then if I do A dot A, I get the magnitude of A squared. Now remember, the magnitude of A can also be written like this. Depends on the textbook you're looking at. And if I do A dot B, that's the same as B dot A. So this property of dot products is actually commutative. And then A dotted with the sum of B plus C is the same as A dot B plus A times A dot C, rather. That's the distributive property. And this property here is the associative property. If I have C times A, so I have a scalar multiple of A, and I dot that with B, I could also do this as C times the dot product of A and B, or A dotted with CB. And 5 says the 0 vector dotted with A, the vector A is 0. Notice there's no vector here. These are all scalars. Okay, so let's look at a few of them and prove them. So like number 1, if I have A dotted with A, that's like A1, A2. If I had 3 components, A3 dotted with A1, A2, A3. So first component times the first component, you get A1 squared, plus second times the second, you get A2 squared, plus the third times the third. Okay, and we know that if we want to, I'm sorry, that's not a 3, that's a 2 squared. Okay, and we know that the magnitude is A1 squared plus A2 squared plus A3 squared with a root over it. To get rid of this root, we square both sides, so we see this is the magnitude of A squared. So that's the proof of the first one. Let's look at a different one. Let's look at maybe number 5. If I have a 0 vector dotted with vector A, well, the 0 vector just has 0 in all its components. I'm just showing one that has 3 dimensions. So A1, A2, A3. If I do 0 times each component, I end up with 0. That was pretty obvious. What about, let's do number 3. What if I have vector A dotted with the sum of B and C? I can write this as A1, 1, A2, A3, dotted with, parentheses, B1, B2, B3, plus C1, C2, C3. So this is A1, A2, A3. Okay, I get B1 plus C1, B2 plus C2, B3 plus C3, like this. And then when I do my dot product, I do the first components together. So A1 B1 plus A1 C1 plus A2 B2 plus A2 C2 plus A3 B3 plus A3 C3. Let's look at this piece, A1 B1, A2 B2, and A3 B3. If I look at those, I can write this as A1 B1 plus A2 B2 plus A3 B3, lumping those together, and then the other ones. So then I have A1 C1 plus A2 C2 plus A3 C3. So I've done all the A's and B's together in the front and all the A's and C's in the back. And if you look at this, wasn't this what you would get if you had a dot product of A and B? So this is A dot B plus A dot C. The proof of that one. We have the dot product where we just combine their components, first times the first plus the second times the second plus the third times the third, and so on. We could also think about this in terms of angle theta. Often this is referred to as the physics definition. We have a theorem that said if theta is the angle between the vectors A and B, then A dot B is the magnitude of A times the magnitude of B cosine theta. So suppose vectors A and B have lengths 3 and 7 respectively, and the angle between them is pi over 4. Find A dot B. So we know A dot B is the magnitude of A times the magnitude of B cosine theta. So the magnitude of A we said is 3, magnitude of B is 7, and then I have cosine of theta. Theta is pi over 4. Well, this is 21, and I know cosine of pi over 4 is root 2 over 2. So A dot B is 21 root 2 over 2. We have a corollary that says if theta is the angle between non-zero vectors A and B, then cosine theta equals A dot B divided by the magnitude of A, magnitude of B. All we've done is taken our theorem and solved for cosine theta. So if you solve for cosine theta, you divide both sides by the magnitude of AB, and you end up with this corollary. So let's do this example. Find the angle between the vectors A, and that's negative 3i plus 7j, and B, which is 2i minus 5j. So angle between them will be cosine theta equals A dot B over magnitude of A, magnitude of B. Let's dot them. And if you need to, you can rewrite this as negative 3 and 7, and B is what, 2 and negative 5? If you dot them, you get negative 6 and minus 35. And the magnitude of A is what? 9 plus 49, which is the square root of 58. We'll do a decimal approximation shortly. Magnitude of B is what? 4 plus 25, square root of 29. So square root of 58 times the square root of 29, and negative 6 minus 35 divided by that, 178.6 degrees. Let's find the angle between the vectors 2, 6, and 3, negative 1. So we're going to do the same kind of thing. We know that cosine theta is A dot B divided by the magnitude of A, magnitude of B. So A dot B is what? 2 times 3 is 6, minus 6. Okay, do you notice it doesn't matter what I'm going to do here? I can find the magnitude of A and B, but I don't really have to because my numerator is going to be 0, which 0 over anything, I still get 0. So I'm really looking for cosine theta is 0 at pi over 2 radians, or 90 degrees, depending on your units. Two non-zero vectors are perpendicular or orthogonal if the angle between them is pi over 2 radians, or 90 degrees. Thus A and B are orthogonal if and only if A dot B is 0. So let's look at this little chart. If theta is between 0 and pi over 2, So if you're looking at your quadrants, A, C, D, S, if theta is between 0 and pi over 2, cosine's positive. So my dot product is positive. If theta is pi over 2, cosine of pi over 2 is 0, so my dot product is 0. If theta is between pi over 2 and pi, I'm in quadrant 2, cosine is negative, so my dot product is negative. What do each of these mean? Well, A dot B measures the extent to which A and B point in the same direction. Okay. So for this first one, if cosine is positive, that means the dot product is positive, so A and B point in the same general direction. If cosine of theta is 0 and the dot product is 0, that means A is perpendicular to B. A is orthogonal to B. And if my dot product is negative, that means A and B point in generally opposite directions. If A and B point in exactly the same direction, which means theta is the same, that means the angle between them is 0, then we have cosine theta, well that's cosine 0, is 1. Which means A dot B is equal to the magnitude of A times the magnitude of B. If A and B point in exactly the opposite direction, that means theta is pi. So if theta is pi, we have cosine pi, which is -1, which means A dot B is the negative of the product of their magnitudes.